Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. We continue talking about spatial data structures here, and in particular we're going to talk about grids. So in the last video, we ran our brute force neighbor finder. We wrote this up. We didn't actually test it at this point. That would actually be a very good thing to do. Maybe after writing this, we'll spend a video writing some test code so we can test both the brute force and what we're going to write this time. So if I go through and have a whole bunch of random data, the idea of the brute force is that it has to check basically all pairs of particles to find all of the neighbors, or for a single particle, what we wrote here is that it goes through and it has to check against every other particle in order to find out what's nearby. This is, well, not all that efficient, and after all, especially if we're in the realm, and this is the assumption we're going to make the assumption that we are searching for a small area relative to the entire thing. If you have to find everything that's within a large circle, that takes up most of the data, well, you're stuck with order n squared for your overall searching, or with order n when you do for a single particle, because you've made it so there are order n things inside of the search radius. So you really can't get around that if you work that way. But for most of the applications where you will use this type of thing, you're searching for a small search radius relative to the size of the entire data set. And so the simplest way that we can make this more efficient is to lay out on our data a grid. And so this is just a graphical representation. I've picked a grid size here so that the number of grid cells is roughly equal to the number of points that we have. So there's pretty much one grid cell per point, which, because the points are not evenly distributed, we have some that are empty here, and then we have others that have multiple. And if we were to add more data points, you can see that the grid cells have to get smaller in order to accommodate those additional data points. So if I wanted to do a search on, say, this point with a grid, I only have to search out inside of grid cells. So the way that we build our grid is each one of these grid cells winds up having a list of particles in it. So this grid cell right here would contain this, this, and this, and its neighbor would contain that one, and this neighbor would contain those two, and I'm not exactly certain where that one goes because it's right at the four-way intersection, and the graphics aren't high enough resolution for me to tell. But if I wanted to find the nearest neighbors of this one, at the very least I have to search these 9 squares, okay? Because it could be right on a boundary, in which case there is no way for me to get away from searching these 4, and it's just easiest if you search in this area. If we wanted to have a larger radius, something that was significantly larger than the cell size, then we would have to kind of branch out and search not just the adjacent 9, but maybe add an extra layer on so that we're in a 5 by 5 and we search in 25 squares, etc. The question is, what order is this? Well, that depends upon a lot of assumptions. Okay? As long as the size of these squares is fairly small, it turns out that in practice, while I drew this so that there's 1 square per data point. For example, in my simulation code, if I were to use a grid, through empirical tests, I found that it's actually most efficient if there are 7 squares per data point. And the reason for that is because normally I'm searching for a fairly small circle around this, and it's simply more efficient to have quite a few empty squares. Then it's more efficient that way than it is to have 1 per square, which means that you'll occasionally get these squares that have large numbers of points inside of them. So what we want to do is we want to write a neighbor finder that, instead of being brute force, is based upon having a grid. So let's come in here, and we're going to make a new Scala class. This is going to be our grid neighbor finder. It's worth noting that the book has code for various neighbor finders, and it uses a more elaborate interface that actually has not just finding for a single point, but also finding for multiple points. Okay, so following our brute force, I'm going to go ahead and copy. Actually, let's go ahead and copy from here on out. Okay, and now this is unhappy because we don't have our one method in there. Okay, so in the case of the grid neighbor finder, when we get the points here, the first thing that we have to do is build up our grid. So I need to make a val that is the grid, and probably the easiest way to do this is to go ahead and write a function called makeGrid that we pass the points to. I'm also going to make the assumption on my grid that my dimensionality is 2. Okay. One of the limitations of grids is that they work very well for 2 dimensions, as we kind of saw here. If you scale this up to 3 dimensions, it still functions, but it turns out that the number of cells that you start having, so for example, a 100 by 100 grid has a nice 10,000 cells in it. 100 by 100 by 100 3D grid now has 1,000,000, and once you go above 3 dimensions, it starts to become non-tractable. So we're just going to make the assumption here that our grid is fixed at 2 dimensions, and when we call distance, we'll be passing in 2 as the value of the dimensions. So, and technically the way I've done this, I'll just say make grid. The question is, what does grid return? Well, based upon our image here, this could be nicely represented as an array of, say, list of A. Okay, so we have an array that holds inside of it arrays, and each one of those has lists of A inside of it. First, we need to figure out how big the array of arrays is, based upon what's in that image. We can go with, say, for example, making 1 grid cell per particle, or roughly 1 grid cell per particle. If we want to do it that way, we will, and I'm going to go with the assumption this is square here, which is not always true, but I'm not going to deal with the additional math there. So my count here, if I'm going to have number of bins by a number of bins, well, then the number of bins is the square root of the number of points, okay, which gives us a double, and I can't make arrays of size double. So there's a function called ceil for ceiling, which basically always rounds up, and that's kind of what I want here. Is I want the next number up as far as the count for how many bins we have. Now at this point, I can make my the grid that I'm going to create, and this is also going to be the thing that I return at the end. And I'm going to use array.fill, and I'm going to make it count by count, and all the lists start off as nil. Oh, and we're going to need to call toInt. Okay, the ceiling gives you back an integer, but it has type double. So we need to explicitly convert that to an int, otherwise we can't make an array using it. And this is unhappy because the type doesn't quite match, so we will specify the type actually nil as a list of A. There. Okay. So now this should be happy. Oh, over here we have a little error because we didn't pass in D, so we can explicitly specify 2. And now I have my array, I have my count, and all I need to do is figure out what values go in what cells. And we're going to break for this video here, and we'll come back in the next video and finish filling in this code.